All right, so welcome back to part 2 of the backend functions. Now, to start with, I'm just going to briefly run through some of the modifications that I made to these functions. One of those modifications was for the position and velocity, and a lot of other things. Instead of having it as as several separate arrays with the x, y, z, vx, vy, vz, whatever, I packed that into a single array. It sort of improves data locality a little bit. So here we can access the x element just by going, 2 times index, and then y is 2 times index plus 1, and so on. So that's how the add function has been modified. If we go to the remove, now originally the way this worked is we sort of scrubbed everything out by shifting all of the data forwards by 1 to cover the spot. But as was helpfully pointed out in the comments, it is a better idea to swap and take the last bit of data on the array and insert it at the deletion position, and this means that we don't have to shift everything. So this is what I'm doing. I'm taking the last element, accessing its data, throwing it into the position, and I'm also zeroing out the last element, setting it all to not a number. Not strictly necessary, but just good practice will help keep the engine more stable. Now, not much else has happened. Oh, also here with the dynamic objects again, chucking all that data into one packed array. And what we're doing here is, where are we? I'm accessing the variables once at the start of the script, then I'm working with those variables, and then I'm writing them back into the array. And again, this just improves data locality by reducing the number of times that these this array indexing occurs. Yeah. Now, with these collision functions, for whatever reason, it's sort of the performance isn't so good. At least for the proper bind function. So I'm actually going to leave that. I won't go through that. I'm just going to stick to the brute force method for collision detection. At least in these cases, it's performing just fine. I can detect collisions between 1,000 spheres in 0.75 milliseconds. And for my purposes, I'm going to be working with a lot less than 1,000 spheres, so I'm happy with that. That's a trade-off I'm willing to make. So yeah, that was just a little overview of modifications that I made to the functions. By the way, we can test these. So as we can see, adding spheres, we can do 1,000 spheres in 0.46 milliseconds. We can do remove 1,000 spheres in 2.23 milliseconds. So not a massive increase. Actually, a lot of this is dominated by inside the tests. It's a Python loop which is running these scripts, not a compiled loop, which is why the performance is a little bit dodgy. But again, for my purposes, I'm going to be working with a lot less than this. Now, this is really weird. This update function, I've been through it. It makes sense, but it is giving me weird results. So I don't know. Let's say update works fine. Okay, so with a proper bind collision check, we're getting up to about 5.38 milliseconds for 1,000 spheres. A little bit unacceptable, I would say. So there are approaches we can take, such as pre-binning the objects so that each object already knows which grid square it is in, and then when we update, instead of checking through, while we change the position, we might as well grab the new grid square and so on. Hopefully that makes sense. But yeah, I was a little surprised by this. It's not so good. whereas the brute force has about the same growth rate, but it gets up to about, 0.78 milliseconds, 0.79 milliseconds, which I think is much more acceptable for this case. So for my purposes, I'm going to go with the brute force algorithm. And yeah, so that's where we are up to at this point. Now, the next few things, I'm going to implement these functions one by one. One of these issues is we've recorded the collision pairs, but we need to actually resolve those collisions. We need to calculate the new velocities for the spheres which collide. So I'll just pop up a bit of an explanation of that process. All right, so I just want to quickly look at one of the mathier parts of the implementation, and that is the sphere-sphere collision reaction system. So in simple terms, let's say we have two spheres and pretend that they're touching each other. And I'll call, just for generality, we'll have these two. Let's say that sphere A is going this way, so it has some velocity, and sphere B is going, doesn't matter. And each of these spheres has a center. So the big picture, the big idea is that velocity is a vector and it can be decomposed. And specifically, it can be decomposed into a component which is parallel to the collision direction, summed with a component which is perpendicular to the collision direction. Now, one of the simplest sorts of collisions is when we have just a straight wall, like aligned along an axis, and then we have a ball that comes along. The collision direction is the normal of the wall that we hit, and we reverse our velocity along that direction. So we keep the direction which is perpendicular is the y-axis in this case, so that y direction stays the same. But the component which is parallel is the x component, and the x component reverses. So when we hit the wall, we just reverse our x direction because it's an x-facing wall, if that makes sense. So that's a simple case. Now in this case, we have, it's slightly more complicated. So our collision direction is the direction vector between the two centers, so from A to B, so position at B minus position at A. And then we have an imaginary collision plane running along through it. So the only direction that we reverse is, the only direction that we reverse is any component of the velocity which is parallel with the normal direction. All right. All right, so how do we determine that? Well, basically, we take the projection, the vector projection, and that is if I take a copy of that AB vector here, and then I imagine dropping this perpendicularly on top, that is the projection of A velocity onto the AB vector. Now, I can't really do that with the B velocity, because the AB vector will be pointing backwards. So what I do is I reverse the direction. I take the negative AB vector and project that part. Okay, so then the idea is that we need to reverse the direction. So what we do is take velocity A and then subtract the projection away from it, and take velocity B and subtract its projection. But then we need to deal with the interchange of energy. So when this ball hits this wall, it bounces off, the wall doesn't move, of course, because the wall has such a high mass and it's fastened in place and all of that. But when ball A rebounds from ball B, some energy is imparted to ball B. So basically what we want to do is we have reduced velocity A by some amount. We then want to add that onto velocity B because of the energy interchange. And similarly, we've reduced velocity B. We want to add that reduction onto velocity A. And yeah, I mean, hopefully that makes sense. So then if we take the original velocity plus the reduction plus the addition from the energy interchange, that is the resultant velocity there. And then same thing here, original velocity B plus the velocity reduction plus the velocity exchanged from A, that is the resultant. Anyway, so hopefully that makes sense, and I'll go through the implementation. Okay, so hopefully that made sense, at least a little bit. Now I'm going to go into the implementation. So one thing I'm going to need is a projection function. Now really my system is two-dimensional, but I'm going to set this up with dummy three-dimensional variables just because, why not? So this is just calculating the dot product by hand for each of these vectors. Now what I want to do is I'm going to modify the contents of W so it is populated with the result of the vector projection of U onto V. So remember, the vector projection is we want to measure how parallel, we want to measure how parallel the vector U is with V, add a normalizing factor, and the result has to be parallel with V. So component by component. So again, what we're doing is U dot V is sort of like a cosine. It's measuring how parallel U is with V. So this will give us a magnitude, and then we multiply it with each individual component to give the direction. So we're actually scaling V according to how parallel U is with it, if that even makes sense. I know gets into a bit of rambling, but there we go. Yeah, and with that extra normalizing factor of the magnitude of V squared. Okay, good. So this will give us the vector projection, and now we just need to use that in our collision function. Okay, so there are 3 steps. The first step I'm going to do is I'm going to fetch the data for each collision pair. So the data, the position and velocity of every sphere, which is involved in each collision pair. And then I'm going to calculate the new velocities. And then finally, I'm going to write those new velocities back into the sphere data. Now, there is an extra optional step which would improve the accuracy a little bit, but it would also take a bit of time, and that is to calculate the proper positions that the 2 spheres should be in so that they're not currently intersecting. However, the velocity calculation, I may revisit this later when I actually get the thing up and running and decide, hey, it doesn't quite look right. But in principle, if the update script is running fast enough, then it should, fingers crossed, take care of that, and the spheres shouldn't be intersecting too much that the calculations become inaccurate. But long story short, there's a parametric equation we can solve to step both of the spheres backwards until they're just touching each other. But I'm just going to leave that at this point in time. Okay, so first step is we grab all the data. Okay, so we're saying, all right, collision indices is of the form index A, index B. So that's a stride of 2. And so if we simply double I, that will give us the A index. So we look that up. And then again, if we double that, that'll give us the X component. Now, again, because X and Y have a stride of 2, to get the Y coordinate, we index into that sphere and then offset it by 1, and that'll be the Y. Okay, now we'll do the same thing again for sphere B, and we get that by offsetting the index within the collision indices by 1, because again, A will be the first of the pair, and then B will be the next of the pair. And then it's very similar. We'll do the same thing to get the velocities of each of these. And then we do a little prayer, but ultimately I won't find out until I run this for real, so that's fine. I'm going to need a few other things. I'm going to need the displacement from A to B, and I'm actually going to work with these. I'm going to build arrays. So as you can see, I am going with dummy 3D arrays by putting in these extra zeros. I know, I felt like doing it. So now we'll get to the velocities. Okay, so what this is doing is we're calculating basically how much velocity did sphere B lose. We take the projection of its velocity in the direction of the collision, basically, as per the discussion that I did earlier, and this will be a positive thing. Basically, velocity B will be going in the same direction as A to B, and so that is how much energy, how much velocity it lost, and that pops onto sphere A. But at the same time, we want to work out how much energy did sphere A lose. And the way we do that is we take our velocity and want to say how parallel is our velocity with the direction of collision. Now, if we don't reverse this, A to B will be in an opposite direction to our velocity, which wouldn't really make sense. So we reverse it, and then we subtract that velocity, subtract that energy away from the sphere. And now we'll do exactly the same thing for sphere B. Okay, so we say how much velocity did object A lose? And we'll add that onto our onto our velocity. And then similarly, how much should we lose? And we will subtract that from our velocity. So hopefully that's looking okay. Don't worry, we don't have to understand it 100%, but yeah, this is what it is. So again, sphere B lost some energy, and that pops onto sphere A in equal opposite amount. Here we lost it. And sphere A lost some energy, and that is thrown onto sphere B. Okay, cool. So now what we want to do is we want to write that data back. So we almost do the opposite here. We're not going to change position. Again, I'm not going to go with pixel perfect collision. Okay, good. So there we have it. The next thing I want to do is just zero out my collision pair to indicate that, yep, the collision is done. The way we do that is we just go to the collision indices, and we'll go 2 times I. So that's the index of sphere A in that particular collision, and then offset that by 1, and we're setting the index of sphere B. So then later on, if we looked in here for that collision pair, we would see negatives, and that's a sign that that collision does not exist. It's been processed. There we have it. Okay, so that is our collision code. It's looking good. All right, so we're almost getting there. There's just 2 more functions I want to work on. One of them is I want to record collisions between 2 different groups of spheres. So I'm going to go with the brute force approach. So I'll grab all of that function. This will basically be a modification of the brute force approach, just to handle a more general case. So what do we do? Handle record sphere collisions groups. I know it's turning into English prose, but that's fine. So what we'll do is we'll have the positions of the members of group A, the positions of the members of group B. Yep, we will record collision indices, and then I'm also going to put in the radius of the members of group A and the radius of the members of group B. And then finally, we'll need 2 different object counts. But yeah, otherwise it's just a simple modification. So we'll pop through here. So I want to look through all the things in group A, grab position A, and then I want to look through all the things in group B, look at position B, and then the test is a distance less than or equal to the sum of the 2 radii? But yeah, that's it. So the way this works is the array will be populated with collision pairs, where the first index is the index of the thing in group A, and the second index is the thing in group B. And then the maximum number of collisions we would have would be, yeah, the size of group A times the size of group B. So we can fill that out in a later video when we look at actually using these functions. But yeah, so there we have it. Okay, so now the final function that I'm going to add at this junction is a function which basically takes a description of a group and populates the set of model transforms which will be used. So we'll have a bunch of spheres for our balls, and the way this will be used is the view class will have a reference to some shared data between the 2 threads, and that shared data will hold the model transforms. It'll read that data and then go ahead and draw them. Anyway, so What I'm going to do is for each matrix, a model transform is a 4x4 matrix, which flattens out to a 16 by 1, like a length 16 array. So I'll write a function which writes portions, 16 numbers at a time, and yeah. I guess because I haven't done a video in a while, I feel like there's more fluff in my explanations at the moment than usual, but I'll get into it, get back into the swing of it pretty soon. Okay, so model transform will be the really large array which holds all the set of matrices. Pos will be the set of position data, x, y coordinates. Now the reason I'm using an offset, most of the time we wouldn't have an offset, but for instance with the balls, the first sphere is always the sphere that the player can touch, can use, and the rest of the spheres are going to be the random balls in the game. So I actually just want to create a bunch of model transforms for the random balls, then I'll handle the other sphere individually because it's going to be one instance draw call for all the members in the group. Yeah, is what it is. Okay, so we're going to have offset. We're also going to have an object count because we need to know how many of these things we're going to generate. Okay, so what I want to go do is I want to say, okay, loop through all of the objects. And just for readability, I'm going to read it out this way. Now the way this works is everything's sort of transposed, so we go row by row. So the first element I'm going to put in here is the first row, and then I'm going to put the second row. Let's get this out of the in the third row. I'll just get this out of the way. So as you can see, this so far is looking like the identity matrix because we're not taking into account rotation of the balls at this point in time. We're just doing their positions. Now the fourth row is where the translation comes in. So we have the X, Y, and Z, and then to maintain the homogeneous coordinate system, we'll put, put 1 there. Cool. So again, the way this would multiply is we'd have 1 times our x coordinate plus this x position times 1 will be our new x coordinate, then 1 times our current y coordinate plus this y amount times 1. You see what I'm saying. So this is calculating the model matrix, and then we'll write that to the model transform array. So the portion we'll write to is, we'll have 4 by 4, so 16 will be our data stride. And there we have it. Cool. So yeah, the reason we're subtracting the offset is, yeah, we want to start from, say, sphere number 7 or something, but we want to take that data from sphere number 7, write it to position number 0, which is why we're subtracting our offset. But yeah, I mean, that's it. We've got our backend functions done for now. I'm happy with that. And yeah, we can move on. So in the next video, we'll be looking at, let's go back to my diagram, we'll be looking at using these with a model class. Okay, cool. See you again soon. Bye.